Well, let's take a look at some things. I want to see if there's any specific problem that you've been having. Since you're the only one here, see if there's anything specifically that you want to deal with before I run through the questions that I selected out of the review document as our samples. If not, we'll get rolling. Let's see. This thing hangs out.
No, I don't have nothing, Professor.
Okay. Let's see. Let me mark that. Close this because my desk isn't big enough. Okay. So first thing I want to do is share the review document so you can see what questions we're looking at. And let's see where here I put it. There you go. Share. Just a second. There it goes. Okay. So I think that's big enough. We can see. And on this first page, I'm going to do the whole front page. There's a variety of there is a variety of questions here that shouldn't overlap much. Okay, so let's take the first one. Scroll it up so it's more visible. You know, I could even make that bigger, because when YouTube gets hold of it, they decrease the resolution. So if I make it bigger, yeah. Okay. Number one. The number of grams in 2.58 moles of sodium carbonate. So the question, of course, you always look for the question, even if it's not in the form of a question. What's it looking for? This question is asking you, what's the mass of this compound if you have so many moles of it? Nine o'clock, junk calls start. Okay, so what do you need to answer the question? If you need to know the mass, and all you're given is the moles, then you're looking at grams and moles together, and that ought to trigger molar mass. Assuming it does, you've got to be able to determine the molar mass of sodium carbonate. Well, you can't do that with English words. You got to write the formula. So sodium carbonate, we know it has sodium, and carbonate is a polyatomic ion. Let me be sure it's there. It should be, yeah, there's the list. Common polyatomic ions right there. So you just look it up, be sure you get the right one, and you find out that it's got a 2- charge. And with sodium's an alkali metal, so it has only a +1 charge and nothing different. It's always +1. So you need 2 of them. So now we have our formula. We can determine the molar mass that's going to be required. Well, other things that are given, I forgot to do that. So the number of moles equals 2.58. Okay, so we need to know the molar mass of sodium. So I need 2 times 24.3, is it? No, excuse me, 23.0. I'm thinking of magnesium. 23.00. Rounded off to 2 decimal places. Then you have 1 carbon. Then you have 3 oxygens. Okay? So we just multiply and add. So the first one is 46, second one is 12.01, and the third one is 48, I think. Yep, 106.01 grams per mole. Now, if I got that wrong, we'll find out pretty quick because there won't be an answer up there for it probably. Okay, so now we want to change this into grams. So this is a dimensional analysis problem, really. Let's see. You want to end up with grams. So that means grams has to be on top here, and moles is on the bottom. And that's the way it is here. So 106 on top, 1, and per mole. So now that's the hard part. That's the thinking part. The rest is just number crunching. And let's see, let's look at the form of the answers. They're all in standard notation. So I'm going to take, my readout is always scientific notation. So I'm going to take the scientific and convert it. My calculator says 273.5058. Right. But we can only keep 3 of them, correct? So we find here, and we look over here, that's 5. So this means that that's 274. And then you go look for the answer, and there it is. 274, D. Now, I noticed that there's a decimal place behind that 4. You don't really need it, right? If that number is non-zero, then it's always significant. Now, for the 300, yeah, if you were to guess 300 and you wanted to keep those 3 significant figures, you'd need that decimal point, because zeros to the right are not significant unless there's an explicit decimal in the number. Okay, that was number 1. All right, number 2. Scroll it up a little bit. I'll tell you what, let me give myself some more room over here. 2. There we go. So, what are we given? 8.52 grams of water is the mass of water. How many molecules of water is that? Okay, so we're looking for, well, actually, we don't have a direct conversion from mass to molecules. It's going to be a chained conversion. I'm going to do this in one step. So if we're going to convert grams to molecules, the bridge between the two is molar mass. Okay, we just go like that, that. So we need moles, right? And then to convert, right, cancel grams, to convert moles to molecules, you need Avogadro's number. Okay. We have to calculate this one. Of course, if you do it often enough, you just know it. Molar mass of water is 18.02 because you've got 2 hydrogens and 1 oxygen. So that's 16, and that's 2.02, 18.02. Now, that's the hard part. So by now, if you didn't already have that skill when you on the first day of class, by now you should be pretty proficient with your own calculator. And we have 8.52 grams divided by 18.02 times Avogadro's number, 6.022 exponent 23. And I get rounded off to 3 significant figures. I get 2.85 times 10 to the 23rd molecules of water. Okay? And that would be A. Let's carry this one step further. How many atoms are in that many grams of water? Well, you need another conversion factor. So molecules is 1. How many atoms per molecule? 1, 2, 3. So just 3 times that number would give you 8.54. Times 10 to the 23rd atoms. Okay? So how many of those are oxygen atoms? How many of them are water or hydrogen atoms? Well, you could go back and do that calculation and say 2 hydrogens per molecule and do the calculation. But I've already got this one. What's the ratio of atoms? There are 3 of them in there, right? So oxygen atoms on this total is 1/3. So I just divide it by 3, and it's got the same number of atoms as molecules, right? Because for every 1 water, you have 1 oxygen. And then what's left over? Well, you subtract that from that, and that's the other 2/3. Or you take 2/3 of that. That's what I'm going to do, I think. No, it's not there. So I'll do it this way. All right, now I got that number in my calculator. And I just take 2/3 of it. So what's 2/3? Well, you can say 2 times 3 divided. Or if you know the decimal fraction, 0.6666666 ad infinitum. So 2/3 would probably be better. And that's 5.69 atoms of hydrogen. Right? That should be double this, roughly, with rounding errors included. Okay, so let's move on to number 3. Okay, 3 out there, and still, yeah, on the board. All right, scroll up a little bit. How many moles of Al2O3 are present in 78.8 grams of this compound? So we got this compound, Al2O3, and we have 78.8 grams of it. So what's the question? How many moles? We want to know moles of this. Okay? It's simple enough. But I want to add a twist. What is that compound? Name it. Is it a type 1, type 2, or type 3? Well, it's got a metal in it, right? Aluminum. So it's got to be a 1 or a 2. But which one is it? A 1 or a 2? Well, look at aluminum. Is it a fixed charge or a variable charge? It's a fixed charge. 3 plus. And you can see it's 3 plus from this. Of course, that doesn't tell you it's a fixed charge. That just tells you what the charge is. But aluminum, in that group, boron, aluminum, gallium, and indium are all 3 plus charge. So they fit into type 1 compounds. So the name is just aluminum oxide. That's it. Okay, now let's go back to the problem. What's the molar mass of aluminum oxide? Well, we look up aluminum, right, on our periodic table, and it's 26.98. So 2 times 26.98. And 3 oxygens. Okay, so we just whip out the calculator, and 26.98 times, and 48 for oxygen is 101.96. Okay, so how do we employ that to find out, to answer this, the number of moles? Well, this needs to be canceled, and this needs to be left over. That's how you do it. So we need to actually flip it and put this on the bottom. Then we can take 78.8 and divide that into it. And I get, see how the answers are given. Well, they're given 2 different ways. Right? So this is the way it shows up in my calculator. 3 significant figures, 7.73 times 10 to the minus 1. Right? Is that one of our answers? Not in that form. But if we change the standard notation, moles. And notice I put a 0 in front of that period, in front of that decimal point. It's not a period. That's why we put a 0 in front of that decimal, because if you don't, you put it in a sentence, it could be mistaken for a period. And if you put the period at the end of a sentence and start your new sentence with that, you think you've got 773 and not 0.773. So that's why that's one of my peeves, is that 0 in front of the decimal. Okay, and that turns out to be A. All right. So let's take a look at number 4. So far, there's been a little bit of crossover, like calculating the molar mass. But for the most part, these have been different problems. Number 4. All right. Question: which of the following compounds has the greatest percent by mass of oxygen? All right. So this is going to take some work. And we need Henry Ford's help, because we're going to do the same calculation on each one of them and compare the percent oxygen value at the end. Right? So let's start off with, how many of them I got? 5 of them. this one here. C. Okay. Rather than write those names up there, we're going to have the formula. That's the only way that you can calculate the molar mass that you're going to need to do the calculation of percent by mass. Remember, when we calculate percent by mass from a formula, you just need the mass of the element divided by the mass of the compound times 100. Now, if you're in the lab and you're doing this, and you have a pure compound and you determine the mass of the element, then you do the calculation. But if you have the formula, then this becomes the molar mass of the element, and this becomes the molar mass of the compound, which includes the mass of the element. That always has the element in it. So that's the approach we're going to have to take, because we're not given raw data, you know, mass of this, total mass. We're given just the compound, and we're not even given that. We're just given the name. So we got to write the compound for each one first before we can use the formula. So the first one, potassium carbonate. This is like the question number 1. Potassium carbonate. CO3 is 2-, and potassium is 1+, so you need 2 of them. Okay? So we're going to do that first. Nitric acid. All right? You have to remember how we name acids. If we say nitric, what do we know about that acid? It has oxygen in it because there's no hydro there. In that case, we look at the nitric and say, what is that derived from? It's derived from the polyatomic ion that has oxygen in it. That's the nitrate ion. And 8s become X. Okay, when you put them in water. Okay, so the other thing we need to write an acid is the proton in front. Acids always start with at least one of those. And since nitrate, look it up in your chart, nitrate is NO3 minus, then we only need 1 proton because that's a plus charge. Okay, so there's the compound for nitric acid. Zinc 2 oxide. Now, is that proper? Do we need to say what the charge of zinc is? Well, we actually don't have to, because zinc is a transition metal, but it's right here, and it only has 1 charge. So it's proper to say it either way. I'll let you guys put the Roman numeral in there, because then you can say, okay, all transition metals are variable charge. We'll put the Roman numeral in. That's okay. I mean, this is a beginning course, but it's proper to say just zinc oxide. But zinc 2 oxide says this: 1 oxygen. A 2+ balances a 2-. That's it. You're done. And that's a type. Well, the way it's written, it's a type 2 compound. But because it's a fixed charge, it's really a type 1 compound. Sulfur dioxide, right? Type 3. Sulfur and oxygen are both nonmetals. So that means you just say how many there are. So we got 1 sulfur, right? You never say mono in the beginning. And dioxide, 2 oxygens. And that's done. Diphosphorus pentoxide is also a type 3. Phosphorus, 2 of them, di, and oxide, penta, is 5. So now we have our compounds written. Now we need to do the percent by mass calculation. Right? So we need both, let's go back to the question. It's asking for percent by mass of oxygen. So we need to focus on oxygen and the percent by mass. Let's see, like that. Calculation says you need to know how much this one there is. 3 times 16. And then in the denominator, you need 2 potassiums. Let's see. Which is 39.10. And these are all grams per mole. Right? So what we're saying is, suppose you have a mole of the compound, right? Just fix it at a mole. Then you actually have 48 grams of oxygen, and you have 78.2 of potassium, plus the oxygen, plus the carbon. So we'll do them in order. Then we'll do the carbon, which is only one of them. And that's why we can do this. Because if they're grams per mole, then you just say, all right, we got a mole of everything. And then the moles go away and you're left with grams. So grams divided by grams gives you mass. And then we have 3 oxygens times 100. Okay, so we can go ahead and do that calculation. So it's 48. And then we're going to add 48 to 12.01 and add it to, what did I say, 78.2? Yeah. So this is 138.21 divided into that one times 100 gives you 34 points. Actually, they're limitless significant figures because we pulled them out of the table. We just rounded them for our own convenience. So you can have as many as you want. So we really only need maybe 3 significant figures. We'll answer the question. Okay. So this is percent oxygen. There we go. Now we just do the same thing for each one. So oxygen here is going to be the same. Divided by, I kind of switched those two close together, didn't I? Hydrogen is 1.01 plus nitrogen, 14.01, and 3 times 16, 48 times 100. Okay, so now we got 48 again on top, and then add 1.01 and 14.01 and divide them. So I get, and times 100, 76.2. Okay, zinc oxide. We only have 1 oxygen here, so that's 16 divided by 16 plus zinc, and that's 65.38 times 100. All right, so 16, and then we add 65.38 and divide 19.7. Okay. Now sulfur dioxide. What does sulfur weigh? Well, we need two oxygens on the top and on the bottom, plus sulfur. Sulfur is 3207.07 times 100. All right, So that's 2 times 16 is 32. And then we add 32.07 and divide that, and we get 49.9%. Okay? And one more. P2O5. So we got 5 oxygens now. Plus 2 phosphorus, which is, look at your periodic table, 30.97 times 100. Okay, so we got 16 and multiply 5 times that. And then we add 30.97 times 2. Added to that gives you that. All right, just checking myself. And divide it times 100. 56.4. Okay, now back to the question. Which has the greatest percent by mass of oxygen? Well, now we just compare the numbers, right? It looks like nitric acid does. Got more oxygen in it than any of the others by mass. Okay? It took a while. I mean, there's a lot of number crunching here. That's why I like to set it up like this so that you do the same thing over and over. And anything that you can help yourself make fewer mistakes is good. All right. So now, number 5. We did that one Tuesday, didn't we? Okay. Well, we can do it again. Or I can change the conditions. Just change the values. Then the answer won't be down here. The answer was, the last time we did it was 57%. But the only choice we had was 60%. So you pick the best one. So I think I will. I'll change the parameters and then we'll see, just work it out the same way. Okay, so this is 5 modified. I'm going to change the parameters. Let's say we have X2Y is good. We'll start off with that. And for that compound, you're given 60% X, but I'm going to change it to 50%. How about 40% X? So this is 40% by mass. That makes this 60%. Okay. And then we want to, the problem says we want to find out what's the mass, percent Y by mass of the compound X2Y2. Well, I want X2Y3. There. So, if this is 40% X and 60% Y, suppose we have 100 grams of that compound. Now we have 40 grams of X and 60 grams of Y in the compound. And how much per X? 20 grams per X and 60 grams per Y. Okay. Now we can go over here and say, well, if you've got 2 X's that means you got 40 grams. And if you have 3 Ys, that means you have what? 180 grams. 3 times 60. Okay. Now, if the question is what's the percent by mass of Y, we just say 180 divided by 180 plus 40 times 100. And see what we get. I get 81.8%. And we've only got 2 significant figures, so it'd really be 82. So just by chance, if that were the problem, then I'd pick C, because it's the closest. That, I didn't plan that. That just worked out that way. But the solution to the problem is that same line of reasoning every time. Okay, so that was 5 modified. Let's see what I've got chalked off for the next one. Okay, we skipped the next page. There must be a lot of repetition on the next page. We'll go to 12. All right, so let's scroll down to 12. Repetition is not bad. In fact, it's good, very good. If you repeat until you get bored. Another indicator that it just occurred to me this morning is whenever I was studying some intensely as a student, studying some topic, some subject, by about the 3rd week of the class, I was dreaming in that topic or that subject. So if you're dreaming chemistry, that's a good sign. So that means your brain's trying to make sense of it and organize it in your sleep so that it's usable. That's my theory about sleep anyway. Okay, so number 12. All right, what's the question? What's the mass of 5.826 moles of calcium hydroxide? Did we do one like that before? Yeah, we did do one like that. Well, we're here, might as well do it. 5.826 moles is given. And they're even kind enough to give you the formula. But is that correct? Right? You know, whoever makes these questions up can make mistakes. So let's check it. Let's see. Hydroxide is a polyatomic ion that has -1 charge. So that's 2 minuses that have to be balanced. You only need 1 calcium because it's an alkaline earth, is always +2 charge. So yeah, that's written correctly. Now we can say, what do we need? Well, in order to get mass, we need to cancel the moles and leave us with grams. So that means molar mass. So calcium is around 40. 40.08. Oops. 40.08. And then we have 2 oxygens. That's the trick in this one. Just you got to remember that subscript has to be propagated through the parentheses. All of these. So you actually have 2 oxygens and 2 hydrogens to give you that total. I think it's going to be close to 100, if memory serves. 32 and 2.02. No, I'm wrong. Yeah, I don't know what I was thinking of. 74.10. And grams still need to be on top. So now comes the easy part. Thinking is the hard part. But don't stop thinking just because you're crunching numbers. Because, I mean, well, you know from experience that I've made mistakes in class. And it dawns on me while I'm doing the calculation and said, wait a minute, this isn't right. So I go back and see what my mistake was. Let's see, 431.182 is at my calculator. Right. And we can keep 4 of them. So that means this one, round that one to 2. 431.2. I got 7 there. 431.7. Well, that's the closest one, and test taking technique says pick the best answer. But why did I get 0.7? Let me check my calculations. 40.08 calcium. Yep, that's right. That's right. That's right. I wrote it wrong. See, 431.7066. I don't know where I got that number. So that was 431.7. I rest my case. Guilty as charged. I had a professor, actually, who was my boss. He used to say, if you know what you did, you didn't make a mistake, because mistakes are undiscovered. So it was a mistake at first, and now that I corrected it, it's not a mistake anymore. All right, that was 12. 13. Choose the pair of compounds with the same empirical formula. Oh, okay. This is a simple one. 15. A, B, C, D, E. Yep. So we got this one and this one. We've got C2H2, C6H6, K2CrO4, and K2Cr2, O7. And we got this one, baking soda, and this one, caustic soda, and this one, just going to take 2 of them, I think. Yep. Okay. So what's the definition of an empirical formula? If that's what we're looking for, we need to know what it means. Right? The empirical formula is the simplest whole number ratio of atoms in your compound. So which one's satisfied? That one can't be simplified anymore, right? Because oxygen's 1 and you can't make it any smaller. How about this one? What would the empirical formula of H2O2 be? HO. Right? How about this one? What's the empirical formula of this one? CH. How about this one? CH. That's the answer. You notice that if you simplify this one to 1, then that would be a half. Right? Or if this is the simplest one, then simplifying this one is impossible because that's an odd number. So that lets that one out, that one out. And this one's got a hydrogen in it. So there's no way that it can be the same empirical formula because you got to have the same elements in each one. Right? So that one's out. And this one's the same thing. It's got an extra hydrogen in it. Right? So B has to be the answer. There's no other choice. How about, let's see, go down to 16. Calculate the number of molecules in 0.000400 grams of gaseous oxygen. And what was that? Was 16. All right, there's the trick. You cannot calculate the number of molecules in that many grams of oxygen unless you know how to write the element. Oxygen is one of those diatomics, right? Like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are all diatomic elements. So when it says oxygen as an element, and here I specified in this question, gaseous oxygen, you know it has to be O2. So the molar mass is 2 times 16. Now we can change this many grams. 0.0004000 grams. So we got to change grams on the bottom and moles on the top. And divide 32 into that number, 0.000432. Right. And, well, that's moles. Right? I'm not finished. It wants to know how many molecules. Your old favorite, Avogadro's number. Right? So I'm part of the way there. Then I need 6.022 exponent 23 times that. 7.5275 times 10 to the 18th. All right, so we've got 3 significant figures right here. So I can keep 7.53 times 10 to the 18th. Now, is that one of my answers? Yep. D. I suspect, what's twice that? 1.51 10 to the 19th. There you go. E. E is the answer you'll get if you just put 1 oxygen there and divide by 16. It gives you a number twice that. Right? So that's, multiple choice question makers are really tricky. They might give you an answer that looks right because that's the one you got. but it's the wrong answer. Right? You got to do it right to find the right answer. All right, that was 16, and then I'm going to skip. We're doing good on time. Skip to 22. We did this one the other day also, I think. But we can do it again, just so it's on the record for our review. People might not want to sit through that practice video, which I've already posted, because there's a lot of dead air in there, like 2 minutes, 5 minutes, sometimes more. So let's do this one for the benefit of our broadcast audience. 22. Let's see. Okay, let's move it over here. And then the question is, what is the molecular formula? Right? So what are we given? We know what I think we know what we need to find the molecular formula. You need the empirical formula first. Then you need to compare the empirical weight to the molecular weight and determine what the multiplier is. All right, so we'll go through that. Acetylene gas is 92.3% carbon. 92.3% carbon and 7.7% hydrogen. Right? And the molecular weight, I'll put it down here, is given as 26 grams per mole. Okay. Right, like all of these percent by mass problems where you have to find the formula, you've got to find a way to get the percent into a mass. What does it represent in mass? Because you can't convert it to moles, and the formula is always a mole ratio of elements. It's not a mass ratio. So we couldn't ratio these two together and find the formula. It doesn't work that way. In fact, that was what was given chemists in Europe fits in the middle of the 19th century. All they knew was mass ratios. And they couldn't figure out what was wrong with their production lines until Avogadro and Cannizzaro came along and solved the problem. It says it's not mass ratio for your formulas and your reactions. It's mole ratio. It's actually, they didn't have moles then. It's numbers of atoms and numbers of molecules that matter. After that, they were flying into the modern age. Okay, so if you got this percentage, why don't we just assume, since it's parts per 100, let's say grams per 100 grams. Right? So let's just assume that there's 100 grams here. Right? If you're not actually given mass, and some problems will do that, they actually give you the mass composition, and then you can calculate from there. You won't have to do this jump. But now, in this case, we have 92.3 grams of carbon and 7.7 grams of hydrogen. So now we have to convert them to moles and find out what their ratio is. Henry Ford again. I know Henry Ford was a rabid racist, but he knew how to build cars. Okay, so hydrogen would be 1.01, because that's the molar equivalent of just one hydrogen, right? We're not talking about diatomic hydrogen, because this is hydrogen in the compound. So now, don't get that confused with free gaseous hydrogen, which is H2. Here, it's just H, 1.01. And carbon is 12.01. Okay, now we can divide those and find out what their mole ratio is. 92.3 and 12.01. 7.6, yeah, three significant figures. 7.69. moles of carbon, and 7.7 divided by 1.01 is 7.62. So within experimental error and calculation rounding error, those are essentially 1-to-1, right? So we know our empirical formula is 1 carbon and 1 hydrogen. What we want to find out is, what is that multiplier? It multiplies by 1 here and 1 there. So it's going to be the same ratio, right? Whether it's C2H2 or C3H3 or C4H4, it's going to be a whole number. It's got to be a whole number. And what we need to do is compare the molar mass for that one, which I call the empirical weight, is 12.01 plus 1.01, which is 13.02 grams per mole. And the molar mass, the molecular weight, is 26 grams per mole. So what's the ratio there? 26 divided by 13.02 is approximately 2. So that's equal to 2, and your molecular formula is C2H2. Okay? Now later when we talk about, I think we're going to talk about bonding, this molecule has 2 carbons in the middle with a triple bond. I know it doesn't mean anything to you now, but that's why there's 2-to-2 or 1-to-1 ratio, because of that structure. Okay, 22, let's see what's next. We should get another one like this a little later, and we'll worry about that. All right, 24 is the molar mass of ammonium phosphate. All right, so to answer this one, it's fairly simple. You just have to be able to write the compound. If you can't write the compound, then you're dead in the water. All right, 24. Ammonium phosphate. This is one of those compounds that's composed, it's a binary compound in my way of thinking. I know the authors think of binary compounds as single atoms, one atom A and one atom B together. But I think of binaries as a cation and an anion. So they could be polyatomics too. And this is the one where you have a polyatomic cation and a polyatomic anion. Ammonium is that. And phosphate is that. Right? So there you have your charge difference, and you got to balance the charges. Remember, polyatomics, you cannot mess with them. You cannot mess with the subscripts. So we need 3 of those, because that charge doesn't belong to one of these atoms. It belongs to the whole group. So you got to treat it as a whole group. Subscript the whole group with a parentheses. So now we can do our calculation. So we need 3 of these and 12 of those. Right? So we have 3 times what? 14.01. Look it up. Yep, that's right. And then 12 times hydrogens. And then 1 phosphorus. I have to look that one up. 30.97. And then how many oxygens? 4. So this molecule is going to have some weight. And 3 times that. And then 12 times 1.01. Right. And then your phosphorus. And then your oxygen. So that's 64. So 149.12 is what my calculator tells me. Grams per mole. Okay, rounding error. Right, 149.09. Pick the best answer. There's no choice in here that says none of the above, right? So you pick the best one. And E is closest to the answer that I got. So I picked that one. All right. Let's see. Where am I going next? That's it for that page. Yes, repetition, repetition. I think we're going to finish early today. There's a lot of repetition in here. '63. Okay, so we'll go all the way down. Let's see if I can do this. Make it quicker. There we go. We're on the right page. 63. This one could be confusing. But don't panic. Right? Ask yourself, what type of problem is this? A certain compound has an empirical formula of NH2O. Its molar mass is between 55 and 65. Right? We're not giving you the exact mass. Its molecular formula is what? Okay, so you have the option, can't calculate it. Can we calculate it? Let's see what we got. We have the empirical formula NH2O. NH2O. So what's the empirical weight for that compound? Well, the empirical weight, let's see, 14 and 2 times 1.01 and 16. Okay. So let's add those up and find out what the empirical weight is, because we know we're going to need it. Right? Anytime you're looking for the molecular formula out of this type of data, you're going to need the empirical weight for that formula. 14.01 and then 2.02 for hydrogen and 16 for oxygen. So that's 32.03. All right. So normally what we would do is divide that into the molecular weight and find out what our multiplier is. Right? We need a multiplier down here to find out what the molecular formula is. Well, since we don't actually have it, all we have is a range, 55 to 65. Okay. Well, we know that the multiplier has to be a whole number. Right? So why don't we just go through it? Say 1 times that is not in the range, right? What's 2 times that? 64? That's in the range. Right? So X equals 2 puts us at 64.06 grams per mole, which is right in the middle of that. Well, that's actually toward the high end of the range. But now we have our X. So our formula is actually N2H4O2. So that's B for this problem. Okay, so we really didn't need to panic. I mean, if it makes you feel better, you can panic, but I'd rather solve the problem. All right. So sit for that page. Let me see. '83. Let's see what 83 has to offer. There's a lot of repetition in here on purpose. 80. Next page. There it is. Okay. 83. See, am I still on camera? Yeah. Okay, that's good. Okay. What's the question? What is the identity of A? Okay. A, what is A? A is an unknown substance. There we go. Unknown substance. So it could be an element, could be a compound. We don't know. It's unknown. So let's look at what's given. Well, we have 12.6 grams of A. 12.6 grams of A. And 35 grams of chlorine gas. $35 grams, 12.6 grams of unknown substance A. Okay. I think unknown substance, based on the way the question is worded, that A is an element, because they're saying you have this much of A and this much of chlorine gas. And then they say substance A contains 1.5 times as many molecules as chlorine gas. What's the identity of A? That's a poorly worded question. You could take that in several different ways. In order to get the answer, what we need is an assumption. We have that much A and this much chlorine. Chlorine gas. Okay. All right, I'm going to clarify it for you. Pardon me. Yeah. Go on, get. It's okay. The cats cause the problem, and my dog looks at me with her ears turned down like she's going to get punished for it. No, that was not your fault. That was the evil kitty cats. Okay, so back to the problem. What the problem should be worded as saying, you have a mixture of 12.6 grams of A and 35.0 grams of chlorine gas. If you've got chlorine gas, it can't be part of a compound of A. All right? So this is a mixture. All right. Now, with that being said, the problem is solvable. Other information that you're given. Substance A contains 1.5 times as many molecules as chlorine gas. So A contains 1.5 times as many molecules as chlorine. Right? So now a solution is shaping up in my mind. What's the identity of A? Well, we're not given enough information to deduce A from just this part of the problem right here. You have to look at the answers and see which answer fits. Okay, so let's proceed. If that's the ratio, then of molecules, let's see, which is another way of saying moles of this, 1.5 times that will give you moles of this. And we've got grams of chlorine gas, so we can find out how many moles of chlorine there is. There are. Get the subject verb together here. So we need to know 35 grams of chlorine converted to moles. Right? So how many grams? What's the molar mass of chlorine gas? Well, one chlorine is 35.45 unless it's changed. Let me see. No, that's right, 35.45 times 2, 70.9. Zero, actually. So this will tell us how many moles of chlorine there are in this mixture. I got 0.494. Of chlorine gas. Now we can calculate how much of this we have, because it's 1.5 times as much. So 1.5 times that is 0.740. 0.740 moles of A. Okay. Now, how do you identify which one of these is the right one? Well, you have to look at what we've got. The information we have now is we've got moles of A and grams of A. We can calculate the molar mass of A. Right? Anytime you have mass of a substance and you know how many moles that represents, you can calculate the molar mass. So the molar mass of A would be this many grams per that many moles. And I get 17.02. 17.02 grams per mole. So we know that's the molar mass. Now all we have to do is calculate the molar masses of each of these and compare them. Well, how do you do that? Well, you just add them up, uranium and 6 fluorines. So you look up uranium. Let's do them one at a time. We can eliminate these without actually having to do complete concentration, complete molar mass calculations. So your choices are A, uranium hexafluoride, oxygen gas, ammonia, boron trifluoride, and carbon monoxide. Okay? So, look up uranium, right? It's at the bottom, down here. It's in the actinide series, the bottom row. One uranium weighs 238 grams per mole. I think we went way overboard on that one. So this one can't be it. Uranium weighs too much. How about oxygen? One oxygen is 16, 2 times that's 32. 32 is too much. Right? Ammonia, 14.01 for nitrogen, and 3 times 1.01 for hydrogen. So that's 17.03. We have a winner. That's the one. If you look at the others, boron is 10.8, so that's not over. But fluorine is 19, right? 19 and 10 would put it way over. Just one fluorine would do it. So that's why this one won't be it. And carbon monoxide is 12 plus 16 is 28 in the neighborhood. And that's too much. So ammonia's it. By exact calculation and by process of elimination, whichever you choose. Okay, that was a fun one. All right. Let's see what we have next. 91. Okay, 91 takes some thinking. Next page, 91, 91, 91. Here we go. Let's get it up here where we can see it pretty good. All right. A compound, well, let's see. What's the question? Which element is element X? Right. So we were looking for an element. Right? What do you need? I mean, how do you identify an element? Right? There are really only two ways. If you know the atomic number, that's chiseled in stone. If you know the atomic number, you know the element. There's no doubt. But if you know the molar mass of the element, or very close to it, you can usually determine it that way also. Because as the atomic numbers go up, the molar mass goes up. And there are a couple of places on the periodic table where you get reversals or you get values that are very close together, so you need a tiebreaker. But in most cases, molar mass will tell you what the element is. So let's see what information we're given. A compound is composed of element X and hydrogen. So it's got X and hydrogen. Analysis shows that X is 80% by mass. So X is 80% by mass. So that means hydrogen is 20%. Right? Okay. And with 3 times as many hydrogen atoms as X atoms. So actually we have 3 here. Like that. Now, here's the assumption that we have to make. There's only one X in that molecule. Right? Problem doesn't say that. But if that's not true, we can't answer the question. Right? Because the answer probably won't be there. Right? We can do a process of elimination right off the bat. Helium, it's not going to form a compound. You just throw it out right off the bat. None of the noble gases typically form compounds. I mean, some have been forced, but helium never got helium to form a compound. I think they've managed a xenon, krypton, argon, and maybe some research team has forced neon. But the larger ones are more likely to form compounds if you force them. But they typically don't like to. So we're really dealing with sulfur, fluorine, carbon, or silicon. So what else are we given? 3 times as many hydrogen atoms as X. Okay, which element is element X? All right, so we're really only given information about the mass. So we've got to determine for X, the question is really grams per mole, right? So let's say we have 100 grams of that compound, like we did before with the 60% thing. If we have 100 grams, that means we have 80 grams of X, and we have 20 grams of hydrogen. Aha! Now we can find out how many moles of hydrogen there are. If there are 20 grams of hydrogen, how many moles is that? Okay. So 1.01 into 20 is 19.8. Moles of hydrogen. Okay, now that we know how many moles of hydrogen is, we can find out how many moles of X there are, right? Because we know the ratio. The ratio is 3 hydrogens for 1 X. And that's why I said you have to assume there's only 1 X, because that won't work. I mean, if it's 2, then it's a different ratio. Okay, so we have to assume just 1 X. So 3 into 19.8 is 6.6. So we have 6.6 moles of X. Now look what we got. We got moles of X and grams of X. So we say 80 grams divided by 6.6 moles equals what? 12.12. All right, is there any one of these elements that comes close to that? What's sulfur? Sulfur is 32.07. It's too heavy. Helium, I mean, even if we hadn't eliminated, helium is only 4. Fluorine is 39, I think. No, 19. Chlorine is 19, right? So that's not it. It's too far away. Carbon. Carbon's 12.01. That seems like a good fit. If silicon is too high, yep, at 28.09, carbon's your best bet. That's the best answer that you can pick out of that group. All right. So that's 91. Let's see where we headed. Skip a page. Skip another page. I might have to come back to some of these. Oh, that's it. I don't have any others marked. So maybe I will look at them. See if there's anything in here that we really haven't covered. Maybe another empirical to molecular weight formula, if I can find one that we have to go all the way through. That would be a good one. So let me see if I've got any candidates here for. Okay, 116. Let's see. Can't get to my scroll bar. Here we go. There. Vinegar. You know, that's not actually true. Vinegar contains, well, that's true, contains carbon, hydrogen, and oxygen. But vinegar is actually a diluted 5% acetic acid is vinegar. Now, acetic acid has carbon, hydrogen, oxygen with a percent of 40% carbon and 6.7% hydrogen. Okay, so that's true. The way it's worded is a little bit off. But let's go with what we got. So we got carbon and we got hydrogen. But we've also got oxygen, don't we? Didn't it say carbon, hydrogen, and oxygen? But we're only given 40.01%. 40.01% carbon and 6.7% hydrogen. So how much oxygen is that? You subtract 40.01 and 6.7 from 100. 53.29. Percent oxygen. Let's see if they add up. Yep, adds up to 100. Okay, so now you know what to do. If you got percent of each one, you got to convert it to grams before you can go anywhere. So you assume 100 grams. That means this is 40.01 grams, 6.70 grams, and 53.29 grams. Now we can find out how many moles of each. Henry Ford again. Grams on the bottom, because they have to cancel. And moles on the top, because our formula is mole ratio, or atomic ratio. Okay, so the magic number for carbon is 12.01 per mole. Hydrogen is 1.01 per mole. And oxygen is 16.00 per mole. So that's a little bit of thinking. Now we're going to do a little calculating. 12.01 is 3.33 moles of carbon. Okay? And this one ought to be close to 6.67. 6.63. Okay? And oxygen, last but not least, is 3.33 also. Okay. So you could probably eyeball this one and see that the ratio is 1 to 2 to 1, or 1 to 2 to 1. But if you didn't see that, some of you, it's difficult to see that. You would divide the smallest one into everything. So divide 3.33 into each one of these. And this one obviously gives you 1. And 3.33 into that one is pretty close to 2. And this one is 1. So our empirical formula is CH2O. So what's the empirical weight? Right? Because we have the molar mass that's given to us. So we had 1 carbon, 12.01, 2 hydrogens, 2.02, and 1 oxygen. So that's 30.03. the molecular weight, they said, was 60. Right? So what's the multiplier? If we multiply that times 2, then we'll get this weight, because 2 times that gives us twice as many atoms. Right? So if we multiply this by 2, we get C2H4O2. That's acetic acid. Now, that is the molecular formula, but we usually write acids with their dissociable hydrogen first. So we'll pull one of these hydrogens out of here, and then we'll write the acetate polyatomic ion on the end. Right? Look it up in your table. That's a -1 charge. This is a +1, so they balance. HC2H3O2. That's because this hydrogen can break away in aqueous solution. Those hydrogens are stuck. They can't move. So that acetic acid, sometimes, in fact, the way I learned acetic acid was like this. That tells you a little bit more about the structure. This would be carbon with 3 hydrogens on it, bound to that carbon. That's the way we write organic molecules. If hydrogens are just to the right of carbon, they're not bound to the next carbon, they're bound to that carbon. And then these 2 carbons are bound together. And then one of those oxygens is doubly bounded, and another one is like that. So there's the proton that breaks away when you put it in water, makes it an acid. But this is technically correct, written this way. And of course, C2H4O2 is A, and that's what they're looking for here, that formula. They don't write it as an acid, right? They just wrote it as the molecular formula. Everything slapped together. Well, let's see. We've been here an hour and a half. And let me see if there are any others that would be instructive. Oops. 113 would be a good one. This is a dimensional analysis problem, and most of them in this course are dimensional analysis. All right, so what's the question? How many atoms of Hg? Right? By this time, you ought to have all those 50 some odd elements memorized. Hg is mercury. So you have a sample of mercury, 60.2 milliliter sample. So the volume is 60.2 milliliters of mercury. And the density of mercury is 13.6 grams per milliliter. How many atoms of mercury do you have? All right. I'll just make a side comment, a side point here. Mercury is a liquid at room temperature. That's what's needed to make a barometer. Torricelli recognized that when he made the barometer. And he knew that if he had by previous experiments, I mean, it didn't just happen overnight. He learned that he would need a tube about 30 feet long, or whatever the measurement was in those days, 30 feet long to make a barometer with water. right? Water was readily available, pure water, in fact, but he wanted something a little more portable. So water has a density of roughly 1 gram per milliliter. Right? So if you find something that's 13 times denser, you can shrink your 30-foot thing down to 2.2 feet. That long, 760 millimeters, actually. So the density matters. That's why I used mercury and not water. Now I've used water in a homemade manometer. It's a curved tube, and one end of it has a tube on it, and I hooked it up to my carburetor on my car. And there was a suction port on the side just for this purpose. So I stuck it on the carburetor, and I could watch the difference in the water levels. When the engine was running, it was sucking air past in the carburetor and decreasing the pressure in the carburetor. And you could measure it with a difference in water levels. The water would drop here and rise here, right? So actually it's the other way around. But the difference would tell you what's the suction in your carburetor. And there are standards, you know, books for this carburetor and that carburetor. If it's running properly, then you should get this much suction at idle. So that's neither here nor there, actually. So now we have these conditions, and the question is how many atoms? All right. So this might be helpful to work the problem backwards. You want number of atoms over here. All right? Number of atoms. How do you get to number of atoms? Generally speaking, you need Avogadro's number. Right? So if you're going to get the atoms over there, it needs to be on top here. But the relationship there is to moles. Okay. So now you got to get to moles over here. So how can you do that? Well, you could use molar mass for mercury, couldn't you? To get to moles. And the molar mass for mercury is 112.41. Okay, so now we got that one done. We got that one's over there. That one's done. We need to cancel grams. Right? So you actually need grams of mercury to cancel these two. Well, how can you get grams out of that? You can get it by this formula. Right? We want mass, so we rearrange it. So now we say density and then volume. Oops. Okay. Now we can get grams of mercury. 81.87. We'll just hang on to some decimal points here. Remember to eliminate rounding errors. So now we take this one, divide by that one, multiply by this one, and we got our answer. So 112.41 divided into that, and then 6.022 exponent 23 times that, and I get rounded off to 3 places. 4.39 times 10 to the 24th. And let's see. Did I read that wrong? Am I looking at the right one? Wait a minute. 4.39 times 10 to the 24th. $2.46. What did I do wrong? We can find the grams, right? Density times volume. They're in the same units, okay? Gotta check that. 13.6. Did I write it down right? 60.2 milliliters. Yeah, that's right. Maybe I punched in my calculator wrong. .187. Oh. Decimal point. Now divide that. And times Avogadro's. .39. I got the same number again. What did I do wrong? 8.187, 112.41, and then 6.022 exponent 23 times. That's 22. All right. There's no right answer there. It's saying 2.46 times 10 to the 24th atoms is the correct answer. You know how to fix that, or how to tease that one out. Go backwards. If the answer is supposed to be 2.46 times 10 to the 24th, then if we divide this into it, that tells us the number of moles. If that's atoms, then we divide this one into that one. So that's 4.085. 4.085 moles. And then we multiply this one right here, flip it so that we can cancel the moles. 112.41 times. So that's 4.59 times 10 to the second power grams. So that's what they're expecting for grams. Oh, of course. There's my mistake right there. I should have recognized that before. 13.6 times 60.2 times 10 squared. But that's not right. Why is it not right? Mercury's not diatomic. If I do that right, I get 7.283 grams, moles. That's moles. No, it's grams. That's grams. And that's moles. 7.283 moles. And then times 6.022 exponent 23. I get 10 to the 24. 4.39. All right, there's no right answer there. I think there's a mistake up here. Instead of 60.2, I bet that should be, if this is 4.59 times 10 squared grams, $33.8. Right? That one needs correction. Now let me look at my worked problems. Maybe that'll give me an answer. Number 113. Maybe I've been working it wrong all this time. Oh, I read the wrong value. Mercury is 200.59. That being the case, that's right. That's right. Now that's right. And this is atoms. Okay, there's nothing wrong with the problem. There's something wrong with the operator. All right, let's leave that debacle behind and see what else I can find. We're coming up on, actually, if we quit at 11, we'll be almost an hour ahead of time. What about this one? 105. Is that still on? Scooch over a little bit. There we go. Okay, 105, let's back up. Here we go. The empirical formula for a compound is C2H5O. So that's the empirical. And the mass, I assume they're saying the mass of the molecular formula is 180 AMU. Is the molecular weight. Now remember, when you see values in the periodic table for mass, it can mean one of two things. It can either mean grams per mole, or it can be atomic mass units per atom. So the calculation is the same, it's just to recognize that this is the molecular weight, and calculating the empirical weight would be in terms of atomic mass units for carbon. So 2 times 12.01 is 24.02, and 5 times hydrogen is 5.05, and oxygen is 16. We've got 45.1. So divide that into that, and what do you get? About 4. Right? So you can get that ratio number from atomic mass units as well as grams per mole. So we would need times 4 would be C8H20O4. And that should be D. Yep. All right. So let me see what else, what other trouble I can get into. All right, we've done that one before. I'm not finding too much here. Might have to let you go. Yep. Because I don't see anything new. There is one in here you may notice that got lines crossed through it. Number 42. The reason for that is I don't know how that problem snuck in here, but it refers to solution concentrations. I don't think we've talked about that yet, have we? Let me see. I don't know. Maybe we have, because I've switched these chapters around over the years. Let me see what we've covered so far. Measurement calculations, chemical foundations, nomenclature. No, we haven't. We haven't talked about solution concentration yet, so that's why I crossed that one out. Okay, let's see, where was I? 42, going backwards. Okay. Well, we could do one more molecular formula. I just passed one of those. We could do 32 just as a final exercise. So let me scroll up here. 32. There we go. Right, so I'm still on camera. It looks like we're good. 32. This will be the last one of the day. compound has a molar mass of 100 grams per milliliter. So we're given that. The molecular weight is 100 grams per mole. Okay? And we're given compositions. Percent composition, and there are no outliers. They've got carbon, hydrogen, oxygen, and that's it. 65.45% carbon. And hydrogen is 5.45%. And oxygen is 29.09%. Okay, so same deal as before. If you know percent, then you know it's parts per 100 or grams per 100 grams. We just say if we've got 100 grams, then we have 65.45 grams of carbon, and we have 5.45 grams of hydrogen, and we have 29.09 grams of oxygen. Now we can find out how many moles there are. Right. Oxygen is 16. Hydrogen is 1.01. Carbon is 12.01. All right. So we've got 65.45, 12.01 divided into that yields 5.45. Moles. Okay. .40. And 29.09 divided by 16 is 1.82. Okay, so here's a case where, see, is that reasonable? Yeah, okay. Here's a case where we don't have an easily definable ratio like we did before. So we need to divide them through by the smallest one. And we can do that because we've established the mole ratio, that much to that much to that much. So if we do the same thing to every one, divide, multiply, it doesn't matter, then the ratio still is valid. This is going to be 1. Right? 5.40, 1.82 divided into it is 2.97. And 545 divided by 1.82 is 2.99. Okay. Let's go back to the question. Determine the empirical formula and the molecular formula. All right. That's what this is for. The empirical formula, this is so close to 3 that it might as well be. So now we have the empirical formula is 3 carbons, 3 hydrogens, and 1 oxygen. We need the multiplier. So what's the empirical weight here? Well, 3 carbons, 12.01, and 3 hydrogens, 3.03 is that one, and 1 oxygen, 16. So that's 55.06. And this one is 100. Okay, the nearest whole number divisor, quotient for this one divided by that one is 2, right? So there's a significant amount of experimental error here. But if we say E equals 2, then we've got C6H6O2. That's why the answer for this one is B. Okay. I think I've exhausted all the possibilities, unless you've thought of something in the process of working all these problems. If something else is bothering you, then we can work it out. Okay. Okay, we're let's see, 47 minutes early. But I don't have any reason to keep you any longer. I mean, I could spring a pop quiz, but that wouldn't be fair because you're the only one here. Plus, we've got all those other students that technically don't have to show up for these. So that's why I haven't given any, one of the reasons I haven't given any pop quizzes that are graded. Just call them practices. Okay, I guess we're done. And upcoming exam on chapter 8, exam 3, will be due Tuesday midnight. So you've got a good bit of time to see. If you do have problems, then contact me. Otherwise, you're probably in good shape. All right, we'll say adios.